Welcome everyone to the Deep Dive. Today we're going deep on something pretty incredible, the Qwen 2.5 Omni model. We've got the technical report fresh from the Qwen team, just came out yesterday, March 26th, 2025.
Yeah, that's right. And what we want to do in this deep dive is really break down this new AI for you and make sure you understand how it can process like all these different kinds of information, text, images, audio, even video.
Right, right.
And then it can respond not just with text, but with really natural, like human-like speech, all in real time. We know you want to understand all of this quickly, completely, and without getting bogged down in all the crazy technical terms.
Yeah, because, I mean, let's be real, the idea of general AI, it's not sci-fi anymore. It's getting more real every day, right?
Yeah.
We've seen those huge leaps with those large language models, the models that can understand audio and respond with language or see images and describe them. But the real game changer, that's a single system that can do it all seamlessly from beginning to end. That's the mountain that Qwen 2.5 Omni is trying to climb.
And the report actually, it lays out some of the major challenges in building this all-in-one model, what they call an omni model. Like, think about it, you have to train it on all these different types of data at the same time.
Right.
And then, especially when you bring video into the mix, you have to synchronize the visual stuff with the sound perfectly. It's all about timing. Then you've got to make sure that when it's generating both text and speech, they work together well and don't, clash or interfere with each other.
Yeah.
And on top of all of that, designing the system that can actually process all of this in real time and then stream the audio efficiently, that is a huge engineering feat.
So let's get into what they've achieved, what they're claiming. According to the abstract, Qwen 2.5 Omni is a unified model that can take in all these different forms of input, the text, audio, images, video, and generate, at the same time, both streaming text and natural-sounding speech. Now, this is where it gets really interesting. They've developed a new positional embedding algorithm. It's called TMOR-PE, specifically made to keep audio and video in sync.
Yeah, and what I think is really fascinating about this TMOR-PE is that it seems to be this critical innovation for dealing with, the fact that video happens over time. It's not just recognizing what's in a video frame, it's understanding when things are happening in relation to the audio track. And this allows the AI to, really grasp the sequence of events in a much more sophisticated way.
Exactly. They've also developed this thinker-talker architecture, which they say is crucial for that real-time understanding and that smooth speech generation. And the report also says this new model, it performs just as well as their specialized Qwen 2.5 VL, their vision language model, and even beats their own Qwen 2 audio in its area of expertise.
And if you think about the bigger picture, that's a big deal, because often when you try to make one model that can do everything, it ends up being, okay at a bunch of things.
Right.
But the fact that Qwen 2.5 Omni can hold its own against models designed specifically for, say, vision and language or just audio, that shows its power and flexibility.
And it gets even better, right? They're claiming state-of-the-art results on those big multimodal benchmarks, like OmniBench.
Yeah.
And get this, they're saying that its ability to follow instructions given in spoken language, it's just as good as if you type those instructions out. They even tested on some really hard challenges like MMLU and GSM-8K.
And this brings up a really important point about how we'll interact with computers in the future. If we can talk to AI naturally and have it understand complex requests just as well as if we type them, well, that could change everything about how we use technology every day.
And to top it off, the speech generation, the talker, it sounds more natural and is more reliable than a lot of other systems out there.
Interesting.
They even mention a metric called WERR on their CTT's evil benchmark. All right, so we got the overview. Now let's dive into the details how this thing actually works.
Okay.
First, the architecture itself.
Yeah. They call it the thinker-talker architecture, and I think that brain and mouth analogy they use in the report that really helps explain it. The thinker, it's like the brain. It takes in all the input, whether you type text, speak audio, show it images or videos. It processes all of that and comes up with a high-level understanding. It also generates the initial text response.
And then the talker, that's the mouth. It takes that understanding and the text from the thinker and turns it into a stream of speech tokens.
Exactly.
Now, the report mentions the thinker is a transformer decoder. Think of this transformer architecture like the model's understanding engine. It's designed to find those complex relationships within the data, allowing it to really think about the meaning of what it's taking in. The thinker also has these separate encoders, specifically designed to pull out information from audio and images.
And the cool thing here is that the talker isn't just like an afterthought. It's described as a dual-track autoregressive transformer decoder. Imagine it like two parallel processing streams.
Okay.
What's really important is that the entire architecture, the thinker and talker together, are trained and used as one single unified model. That end-to-end design, that's really important for how it can do all these integrated things.
So the brain and the mouth are connected, working together. How does this brain actually see and hear? Let's talk about how it perceives these different types of input.
All right, for text, they're using Qwen's tokenizer. It's this byte-level, byte-pair encoding system. It's got a massive vocabulary, over 150,000 unique pieces of text. This means it can represent and process a huge range of written language really efficiently.
Makes sense. What about audio? And I'm including audio that's part of a video here.
So for any audio, first they resample it to a consistent 16 kilohertz. Then they transform that audio into a 128-channel MEL spectrogram. You can think of this like a visual representation of the different frequencies in the audio over time. They use a 25 millisecond window and a 10 millisecond hop in this conversion. And what's interesting is they're using that same audio encoder tech from their Qwen 2 audio model. So each little chunk of the audio that the model processes, that represents about 40 milliseconds of sound.
So it's breaking down the audio into these tiny time segments. Now, what about images and videos that don't have audio?
For that, they're using the vision encoder from their Qwen 2.5 VL model. And this is a big piece of tech. It's a vision transformer with something like 675 million parameters. It's been trained on a massive amount of still image and video data. So it's got a really good foundation for understanding what it's seeing, both static and moving visuals. Now, to handle the fact that videos can have different frame rates, like some might have more pictures per second than others, they use a dynamic frame rate for video. And here's a neat trick. They treat each still image as if it were two identical video frames back to back. This helps make the input consistent for both still images and videos.
Oh, that's smart. So still images and videos all handled in a unified way. Now, this TMROPE, this sounds super important, especially for videos with audio. Can you explain how that works?
Yeah, so TMROP, it stands for Time-Aligned Multimodal ROPE. It's how they encode the three-dimensional positional information, so that's time, height, and width, within all the different types of input. They took the original rotary embedding technique, MROPE, and modified it in a clever way to keep track of these three dimensions.
Okay, so how does each type of data, the text, audio, image, video, how do they actually use this PMROPE?
Okay, so for text, it's pretty simple. The temporal, height, and width parts of TM-ROPE, they all use the same position IDs. So for text, it works just like the regular 1D ROPE you see in other language models, just keeping track of the word order. Now for audio, they also use the same position IDs across all three dimensions, but they add an absolute temporal position encoding on top. So here, one temporal ID is exactly 40 milliseconds of audio, matching that frame size from their audio encoder. This gives the model a very precise sense of the timing within the audio.
Makes sense that direct time link is essential for audio. What about for still images then?
With images, because it's just a single moment in time, the temporal IDs for all the visual tokens, they stay the same. There's no progression through time in a single image. But they do assign different height and width IDs to each visual token based on where it is in the image. This lets the model understand how things are spatially arranged in the picture.
Okay, and now the complex one. Video that does have audio. How does TMROP handle that synchronized audio and visual information?
So the audio part is encoded just like we talked about for standalone audio with those 40 millisecond temporal IDs, but the video is treated as a sequence of individual image frames. And for each of those frames, the height and width IDs are assigned just like for still images. But here's the key. The temporal ID for each frame, it goes up, it increments as the video plays. And because different videos can have different frame rates, they adjust these temporal IDs dynamically based on the actual time passed between frames. This dynamic adjustment is important because it ensures that whether a video plays at 24 frames per second or 30 frames per second, one temporal ID in the model always represents that consistent 40 millisecond window, keeping the visual timing perfectly aligned with the audio.
Ah, the dynamic adjustment. That's brilliant, keeping everything in sync. Now, what happens when you have different types of input at the same time? Like if you give it text and an image, how does TROP handle the positional numbering in that mixed scenario?
So in those cases, when you have multiple types of data, the numbering for each new type, it just starts by taking the highest position ID from the previous type and then keeps counting up from there. So you have this continuous sense of position across all the different data types, no confusion about where things are in space and time relative to each other.
So it's building this unified sense of space and time across all these different data streams. The report says this TMROPE approach really improves the model's ability to understand those positional relationships and integrate these different modalities. Now, they also talk about this specific technique for video with audio, the time interleaving method. What is that exactly?
Yeah, this is interesting how they handle video with audio. What they do is they split the whole audiovisual sequence into little chunks, each one lasting 2 seconds in real time. Within each of those chunks, they process the video part first, all those frames that occur in that 2 second window, and then right after that, they process the audio for that same 2 second interval. By interleaving the visual and audio like this in sync with the time, it gives the model a very structured way to learn the relationships between what it's seeing and hearing.
So they're not just throwing all the video and then all the audio edits separately. They're structuring it carefully in these time-aligned chunks to help it make sense of the connection.
Exactly.
All right, so the thinker has processed all this input, maybe generated some text. How does the talker actually create the speech?
Right. So the talker gets two key things from the thinker. First, it gets those high-level representations, that deep understanding that the thinker has built from the input. And second, it gets the embeddings of the text tokens that the thinker has produced in its text response. This combo of understanding and specific words, that's really important for generating natural-sounding speech.
Why is it so important to have both that understanding and the specific text tokens?
Well, if you think about creating speech in real time to have a natural expressive delivery, you need to know the tone, the emotion, the overall attitude, even before the entire text is there.
I see, I see.
And those high-level representations from the thinker, they carry this kind of information. They capture the meaning and context, allowing the talker to start shaping the speech even as the full sentence is still being created. However, while those representations are great for meaning and emotion, they might not have enough detail about the specific sounds, the phonetics.
Right.
Words with similar meanings might have very similar representations, even if they sound different. That's where the text tokens come in. They give the precise info about the exact words being said, no ambiguity about the sounds.
That makes a lot of sense. You need the emotional and semantic context from the thinker to guide the delivery, but the precise phonetic information from the text to get the pronunciation right. Now, the report also mentions this efficient speech codec. It's called Qwen tokenizer. What's its role in all of this?
So this speech codec is designed to take all the rich info about speech, the sounds, intonation, rhythm, and represent it in a compressed, efficient way. The cool thing is that this compressed format can be decoded back into a stream of speech in a way that we call causal.
Causal.
Meaning it can be done piece by piece, sequentially, which is super important for streaming. So the talker, after it gets the understanding and text from the thinker, it starts generating both audio tokens using this codec and the corresponding text tokens. Importantly, the researchers say the speech doesn't have to be perfectly aligned with the text, like word for word or with exact timestamps. This flexibility actually makes things easier for both the training data and the real-time generation process.
So it's not aiming for each syllable at a precise microsecond. It's more about capturing the flow, rhythm, and the emotion of the speech. Now, since they're going for these real-time interactive experiences, streaming is obviously a big deal. What did they do specifically to enable that efficient streaming of audio and maybe even video down the line?
You're right. That initial packet latency, the delay between when the input comes in and when the output starts flowing, that's a major concern with streaming.
Yeah.
And the report actually breaks down the different things that contribute to this delay. You've got the processing time for those multimodal inputs, the lag until the very first voice token is generated, the time to convert that speech segment into actual audio, and the inherent processing time of the model itself. So they've made optimizations in all of these areas.
Let's start with what they call support pre-filling. What's that about?
So support pre-filling, that's a common technique in AI to speed up the initial processing. To make it work well with multiple types of input, they've changed both their audio and visual encoders to use blockwise attention along the temporal dimension, so over time. For the audio encoder, instead of processing all the audio at once, it now does its calculations in smaller 2-second blocks. And for the visual encoder, they're using something called flash attention. They've also added this MLP layer, a multi-layer perceptron, which merges those adjacent 2x2 tokens in the visual representation into a single token, and they set the patch size for processing images to 14, which helps with handling images of different sizes.
Okay.
So by breaking down the input into smaller chunks, they can start processing and responding much faster, reducing that initial delay.
Makes sense. Yeah. What about generating the actual speech stream, the streaming codec generation?
Yeah.
How is that optimized for real time?
So for that, they've used a sliding window block attention mechanism in their flow matching DIT model. That's denoising diffusion transformer. This DIT model generates the MEL spectrogram, that visual representation of the audio frequencies, from the compressed speech codec tokens. And this sliding window mechanism, it limits how far back and forward the current token can look when deciding what to generate next. They group those audio codec tokens into blocks, and the DTICE receptive field, its ability to see context, it's limited to just 4 blocks, 2 in the past, the current one, and 1 in the future.
So it's only considering a small window of surrounding audio context at any given time.
Exactly. And when decoding, they generate that MEL spectrum chunk by chunk, ensuring each chunk has access to those necessary context blocks. This keeps the speech quality and coherence high, while still generating it piece by piece for streaming.
Got it.
They also use this chunk-by-chunk approach with their modified Big VGAN to reconstruct the actual waveform, the raw audio, from the generated MEL spectrogram, making the audio streaming even smoother.
So processing in small, localized chunks with this limited attention span is key for getting that audio out quickly and smoothly. Now let's step back and talk about how they built this amazing model from the ground up. What was the initial pre-training process like?
So they pre-trained Qwen 2.5 Omni in 3 distinct stages. In the first stage, they kept the large language model, the core text processing part, completely frozen. Their focus was just on training the vision and audio encoders. They used a massive data set of paired audio and text and images and text to really build up a strong understanding within that frozen LLM.
So the vision and audio encoders were learning to extract meaning from images and sounds in a way that the language model could then understand and connect to text.
Exactly. Then in the second pre-training stage, they unfroze all the model parameters, the LLM, vision encoder, and audio encoder, and trained the whole system on a much broader set of multimodal data. This included image text and audio text pairs, but also video text data, video audio data, and of course lots of plain text. They emphasized using multimodal datasets that also had multiple tasks, helping the model learn to reason across modalities.
So that second stage was where it really started to learn the connections between these different types of information. What about the third and final pre-training stage?
Right, so the final stage was all about getting the model to understand very long sequences of data. They trained the whole thing with input sequences up to 32,000 tokens long. The report says this really helped it with tasks that need you to understand long-range dependencies and maintain context over longer periods.
Wow, that's huge. And they mentioned their pre-training data set was very diverse, using natural language prompts to describe the data, similar to what they did with their Qwen 2 audio model.
Yeah, they moved away from using structured tags to describe the data and used these natural language prompts instead. This helps the model generalize to new situations and better follow instructions given in natural language. They also gave some details about how they initialized the different parts. The LLM started with the weights from their Qwen 2.5 model, the vision encoder from Qwen 2.5 VL, and the audio encoder was based on the Whisper Large V3 architecture. And interestingly, they first trained the encoders and their adapter layers separately with the LLM frozen. Only after that did they start the joint training.
So a very carefully staged approach, likely to keep the training stable and efficient. They also mentioned the sheer amount of data used in that second phase. That's incredible.
It was a massive data set, yeah. Something like 800 billion tokens for image and video data, another 300 billion for audio, and another 100 billion specifically from videos with audio. They also said that in earlier stages, they were limited to 800 Hef192 tokens in length, which they then massively expanded to that 32,768 limit in the last stage to handle those really long sequences.
So a very well-planned pre-training process. What happened after that? How did they fine-tune the model to handle specific tasks and have more natural conversations?
Well, they use the ChatML format extensively for instruction fine-tuning. That's a way of structuring conversational data to train the model to act like a helpful assistant. It's got turns between a user and the assistant, and for this multimodal model, they've got special tags to show where visual content starts and ends within the conversation.
So teaching it to have conversations that involve not just text, but also images, audio and video.
Right. They fine-tuned the thinker with this ChatML format on all sorts of data. Text conversations, conversations with visual input, with audio, and mixed ones with multiple types of input. The talker, the speech part, got its own three-stage fine-tuning process.
Tell me about those stages for the talker.
So the first stage focused on context continuation. This means teaching it to continue a spoken sentence naturally based on what was said before, making the speech flow smoothly. The second stage used something called direct preference optimization, or DPO, to make the generated speech better and more stable overall.
DPO, how does that work for speech?
They basically made sets of training data with an input, a good speech output, and a bad speech output. These examples were ranked based on automatic scores that looked at things like the word error rate, or R, which measures how accurate the words are, and the punctuation pause error rate, which looks at how natural the pauses and intonation are. So DPO encourages the model to generate speech more like the good ones and less like the bad ones.
Oh, that's smart. Steering it towards better speech. What about the third and final stage for the talker?
That was multi-speaker instruction fine-tuning. Here the goal was to improve the naturalness of the speech even more and make it more controllable. Maybe adjust the style or mimic different voices. They also used in-context learning, or ICL, for the talker.
In-context learning for speech. Interesting. How does that work?
They basically trained the talker to continue speech, predicting the next token, using a data set of multimodal dialogues with spoken responses. This helped it learn to map meaning to actual sound, and also how to express things like rhythm, emotion, and even accents, all depending on the conversation.
Wow.
They also mentioned using techniques for timbre disentanglement. This helps prevent the model from associating specific voices with specific words, making the voice generation more flexible.
So a very thorough fine-tuning process, focusing on both understanding and generation, even getting into those subtle details of how we speak. Now, how did Qwen 2.5 Omni actually do in real-world tests? Let's start with its understanding and text generation abilities, what they call X-to-text performance.
They tested it extensively. For text-to-text, they compared Qwen 2.5 Omni to other similar language models, around 7 billion parameters. It generally performed between their previous Qwen 2.7b and their Qwen 2.5 7b. But what's interesting is that it beat the older Qwen 2.7b on most of the benchmarks they used, like MML Pro, MML Redux, Math, GSM8K, MBPP, MultiPLE, and Live Code Bench. These benchmarks test all sorts of text understanding and reasoning skills.
Okay, and what about when the input was audio to text tasks?
For audio to text, they looked at general understanding, which includes speech recognition and speech-to-text translation, audio reasoning, and interactive voice chat. Qwen 2.5 Omni did as well as or better than other top models on standard benchmarks like Flourish, Common Voice, and Covos 2. It even beat previous leaders like Whisper Large v3 and their own Qwen 2 Audio in some cases. It also did great on more general audio tasks like classifying music and vocal sounds, and on audio reasoning tasks using their MMAU benchmark.
That's really impressive. So it understands spoken language really well. What about images? Image to text, where it has to describe an image or answer questions about it.
For that, they focused on tougher tasks like college-level reasoning, math problems based on images, general visual question answering, and optical character recognition, or OCR, within images. They compared Qwen 2.5 Omni to their own Qwen 2.5 VL7B model, other Omni models, and even OpenAI's GPT-4 Mini in some cases. It did about as well as Qwen 2.5 VL7B and got better results than other publicly available Omni models on a bunch of benchmarks.
Wow.
Things like MMMU, MathVision, MBench, TextVQA, DocVQA, and ChartQA. It even beat GPT-4 Mini on many of these. They also highlighted its visual grounding skills, meaning how well it can identify and refer to specific objects within an image.
That's really good. And what about videos without audio?
For video without audio, Qwen 2.5 Omni again outperformed other open-source Omni models and GPT-4 Mini. It was competitive with their Qwen 2.5 VL7B model on benchmarks like Video MME, MVBench, and EgoStima. So it's good at understanding the content and how things change over time in video.
And lastly, what about those truly multimodal inputs, like an image and a spoken question together?
On the big multimodal benchmarks like OmniBench, which test how well a model understands and reasons across different modalities at the same time, Qwen 2.5 Omni achieved state-of-the-art performance, much better than other Omni models. So it's really good at integrating and understanding information from different sources.
It sounds like it excels across a wide range of tasks. Now let's look at its speech generation, its X-to-speech capabilities.
Right. They focused on zero-shot speech generation, where the model hasn't specifically trained on a voice, and single-speaker generation, where it's been fine-tuned on one person's voice. In zero shot, Qwen 2.5 Omni did very well in terms of content consistency, measured by whir, and speaker similarity, measured by SIM, on the seed benchmark. It was even comparable to dedicated zero-shot text-to-speech systems. They also said the generated speech became much more stable after adding reinforcement learning to the training.
That stability is so important. It makes the speech sound much more natural. And what about when it's been fine-tuned to imitate a specific person's voice?
So in single speaker generation, they compared the model before and after fine-tuning, even against real human recordings. The fine-tuned model could capture the rhythm, intonation, and emphasis of the target speakers really well while staying stable. They said it got close to human-level quality, both in how natural it sounded, using a metric called NMOS, and how accurate the content was, using whir.
That's incredible. AI speech, almost indistinguishable from human speech. So bringing it all together, what are the key takeaways from our deep dive into Qwen 2.5 Omni for our listeners?
The big one is that Qwen 2.5 Omni is a truly unified model, understanding and generating across multiple modalities, including real-time, natural-sounding speech. Their new TMROP algorithm seems to be crucial for integrating and synchronizing video. And the thinker-talker architecture is successful at generating speech in real time without the text and voice outputs interfering with each other. They've also used blockwise encoding and sliding window attention for efficient streaming of the audio and potentially video in the future.
And it seems to excel at those complex audio-visual interactions and conveying emotion through its speech.
Exactly. And the results show that it not only performs as well as similarly sized models specialized for a single modality, particularly in understanding and responding to voice commands, but also achieves state-of-the-art results on those tasks that require understanding multiple types of information.
That's really impressive.
The report also points out some areas that need more work, like video OCR and better audiovisual collaboration. They say we need more research in these areas, maybe through collaborations between academia and industry, to create better benchmarks and datasets. Ultimately, the Qwen team believes that Qwen 2.5 Omni is a significant step towards AGI.
Fascinating.
Their goals for the future include making the model more robust and faster, and also expanding its output capabilities to include things like images, videos, and even music.
This is absolutely amazing stuff. Qwen 2.5 Omni is clearly a huge step forward in the world of multimodal AI. Now, our listeners, you have a much better understanding of its capabilities, how it's built, how it handles different types of data, how it's trained, and how well it performs in a wide range of tasks. So here's something to think about. With an AI that can understand and respond in such a human-like way, using multiple modalities, what completely new applications and interactions might be possible, things we can't even imagine yet. What are the potential changes this kind of advancement in AI could bring to society? Think about these possibilities, maybe even explore the technical report yourself or look into related research to continue your own deep dive into this exciting field. Thanks for joining us on the Deep Dive.